to the next session on virtual labs. In this session, we are going to see the 7th experiment of Machine Dynamics and Mechanical Vibrations Lab. The title of the experiment is 2 degree of freedom, forced vibration. The aim of the experiment is to understand the application of force excitation on the 2 degree of freedom spring mass system and observe its characteristics by varying its different parameters. Analyzing real system as a single degree system is an approximate assumption. Because real system has more than just 1 degree of freedom and are also very rarely linear, it requires several degrees of freedom for a meaningful model. Hence, a simple 1 degree of freedom system analysis is not much helpful in studying the characteristics of the system. A natural extension of single degree of freedom system is to consider the system as 2 degree of freedom models. A system that requires 2 independent coordinates to describe the motion is called 2 degree of freedom systems. For example, if there is a motion along the x-axis and also along the y-axis at the same time, then we say that there is 2 degree of freedom. If there is motion along only one axis, then we say it is 1 degree of freedom. And if the object is free to rotate in many dimensions, then we say it is multi-degree of freedom. Here we have shifted from 1 degree of freedom to 2 degree of freedom. The reason being, most of the machines in the universe are not based on 1 degree of freedom. Obviously, there will be a second degree to it, hence the requirement of this study. Some practical examples of 2 degree freedom systems are shown below, like as forging hammer anvil supported in its base. You can see here, this is the actual figure and this is a 2D figure drawn here. You can see here, this is the anvil which is supported in this frame. There is an elastic pad attached here, obviously for absorbing the vibration caused by the falling of an object on the anvil. Below that, there is a foundation block, and finally there is a soil. So you can see these are actually acting as dampers, such that you are not allowing a lot of vibration to pass to the other objects around it. These are also called as isolators, which means that you are not allowing vibration to pass. There is some isolation created. So we are studying about the forging hammer anvil supported in its base, which in turn is supported on ground isolators. As you can see here, it is supported on ground isolators. A reciprocating engine with dampers. So a reciprocating engine can also have dampers attached to it. A relatively light shaft with 2 discs as in a turbocharger rotator. A generator driving a motor through a coupling. So this is a generator, this is a motor, there will be some coupling in between, and there will also be some amount of vibration, and there will be 2 degree of freedom, not 1 degree of freedom here. For a 2 degree of freedom system, there are 2 equations of motion, each one describing the motion of one of the degrees of freedom. In general, the 2 equations are in the form of coupled differential equations. A simplified 2 degree of freedom system is shown below. This is the system like these. There is a mass here and also a mass here. It is connected via springs, and this is the fixed end. The motion of the system is completely described by the coordinates, and x1 is a function of time and x2 is also a function of time. x1 is the displacement of mass 1. It's a function of time, and x2 is the displacement of mass 2. It's a function of time, which defines the positions of the masses m1 and m2 at any time t from the respective equilibrium positions. So these are the equilibrium positions, and x1, x2 will show their position at a particular instant of time. The external force F1t and F2t are the respective forces at the masses m1 and m2. Equations of motion of 2 degree of freedom system are given by mx double dot plus cx dot plus kx is equal to cy dot plus ky. There is some form of input to the system, and that equation is here. Some force is given, forced vibration, as we have already discussed in base excitation. This was the equation used for base excitation. Now when I talk about m2, it is here. This is m2 x2 double dot plus k2. x2 minus x1 is equal to F2T. This is the force which is exerted at the second end. Now suppose if we talk about the free vibration analysis, for the free vibration analysis of the system shown above, if we set F1 and F2 to 0, the equations above reduces to these equations. This was F1 which has now become 0 and this F2T is also 0. So these two equations are written in this form. Let us assume the solution for x1 and x2 under steady state conditions as harmonic excitations with the same frequency and phase angle but with different amplitudes and are given by these two values. These phase phi is same, you can see here, only this magnitude, the amount of excitation that you give to both of them are different. So for the first mass where the displacement is x1, your capital X1 is used, and for the second mass where the displacement is x2, your capital X2 is what you can see. Both are giving sine form of input to the system. By substituting the above equations in the equations of free vibration, we have these two equations. This x1 and x2 have been differentiated or substituted the way it is as per the requirement, and these two equations have been obtained. The natural frequency of vibration of the system is found by solving these equations and is given by. So omega is calculated as omega n1 square and omega n2 square with this equation. Resonance occurs when the exciting frequency coincides with any one of the natural frequency of the system. This is something that we already know. Forced vibration analysis. In case of forced vibration of the simplified 2 degree of freedom system shown above, the system could be excited by either of harmonic forcing functions F1 or F2. So either one of the two can cause some kind of disturbance. But for the specific case, we assume the system is excited by harmonic force F1 is equal to F0 sine omega t. This is the force that we are going to use. The equation of motion of the 2 degree of freedom system reduces to this equation. You can see here, this equation which was 0 has now taken up the value F0 sine omega t on the right hand side, and for the second one, it is still left to 0. When the harmonic forcing function acts on the system, the solution consists of transient part and the steady state part. In steady state part, the vibration of any point in the system takes place at the frequency of excitation. Let us assume for the steady state, the solution is of this form, like we assumed before. Same solution is assumed here. Substitute x1, x2 in these two equations. You will get these two new equations now. And by solving the above equations, we get x1 and x2 in these form. The above two equations, this capital X1 and capital X2, give the steady state amplitude of vibration of the two masses respectively as a function of forcing frequency omega. So this is a very simple theory given for what is 2 degree of freedom and what are the equations used for calculating the steady state amplitude. Now we'll see the procedure. Edit parameters in the variables toolbox and observe changes in the dynamics of the 2 degree of freedom system shown in simulation window. So this is the window that is going to appear in simulation tab, and we can change these variables F0, omega, K1, M1, K2, M2, and this is the controls tab where we are going to get the results. Now see here the variable toolbox, all these are the variables and what they are is given here. Like F0 is the force, K1 is the spring constant of the first body, K2 is the spring constant of the second body, this omega is the speed, M1 and M2 are the mass of first and second body respectively. You will have these kind of controls. You can have either pause or play, or you can shift to the next slide. So when you click on the experiment, you're going to get some kind of results here because of the values that you choose. So let's go to simulation now. Before that, there is a self-evaluation tab. You can just go through these questions. They are very simple. In the simulation tab, we will change the value of F0 to 650. Omega, suppose we keep it to 4.33. And K1, I'll change. Mass is 240. K2 is 500. I'll leave it as it is. M2 I'll change it to 36. The equations which we studied are actually determining these kind of amplitude. Now we will go to the graph and we'll see. This is x1 by xst. Xst is the static deflection. X1 is the dynamic deflection of the mass 1. It is plotted over the frequency ratio, and also we can calculate x2 upon xst versus the frequency ratio. So these are for these particular values that I have set. You can change the values and you can get some other results. Like you can see here, I'm changing the value of M2. I'll change K2, M1, K1. So this is X1 upon XST for the changed values now. And also this is X2 upon XST versus the frequency ratio. So that's how you are going to analyze and get the graphs. After that, there is a tab for assignment. You can just go through the question and solve it. Then there is another quiz given here. Next comes a video which will explain the same thing as I just told you. Then there is references given for this experiment. And finally, there is a feedback section to share your experience regarding the experiment that you have just done. So with this, I end the session. I hope you have understood how to analyze 2 degree of freedom forced vibration using virtual lab. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.